Part 1. The Birth of Black Holes. What if somewhere in the universe there exists a place where the laws of physics break down completely? A place where gravity becomes so powerful that even light, the fastest thing in existence, can never escape. A place where time slows down, stretches, and eventually stops entirely. These places are real. They are called black holes. Black holes are among the most mysterious and terrifying objects in the universe. They are invisible regions of space where gravity has become so strong that nothing can escape once it crosses a certain boundary. Not matter, not energy, not even light itself. But the most shocking fact about black holes is that they are not rare. Scientists now estimate that there may be hundreds of millions of black holes in our Milky Way galaxy alone. Across the observable universe, the number could reach trillions. For something that seems so exotic and mysterious, black holes are actually a natural result of how stars live and die. To understand black holes, we must begin with something much more familiar: a star. Every star you see in the night sky is essentially a gigantic nuclear reactor. Deep inside its core, temperatures reach millions of degrees, and pressures become so extreme that atoms are forced together in a process known as nuclear fusion. Hydrogen atoms collide and fuse together to form helium. This process releases enormous amounts of energy. That energy pushes outward against the crushing pull of gravity. Gravity constantly tries to collapse the star inward. Fusion constantly pushes outward. For most of a star's life, these two forces remain perfectly balanced. This balance can last for millions, billions, or even trillions of years, depending on the size of the star. But no star burns forever. Eventually, every star runs out of fuel. And when that happens, gravity begins to win. Small stars like our Sun die relatively peaceful deaths. In about 5 billion years, the Sun will expand into a red giant and eventually shed its outer layers, leaving behind a small dense core known as a white dwarf. But massive stars live much shorter and far more. Instead of lasting billions of years, these giants may live only a few million years. Inside these massive stars, fusion continues, creating heavier and heavier elements. Hydrogen becomes helium, helium becomes carbon, carbon becomes oxygen, oxygen becomes silicon, and eventually the core begins to produce iron. Iron is the end of the line for stars. Unlike other elements, iron does not release energy when it fuses. Instead, it absorbs energy. The moment a star's core becomes iron, the nuclear engine that has been holding the star up for millions of years suddenly shuts down. The outward pressure disappears almost instantly. Gravity, which has been trying to crush the star for its entire life, suddenly faces no resistance, and the collapse begins. Within less than a second, the core of the star begins. Electrons are forced into protons, forming neutrons. The core of the star shrinks dramatically, sometimes collapsing from the size of Earth to a sphere only a few kilometers across. Meanwhile, the outer layers of the star are still rushing inward at tremendous speed. When they collide with the dense collapsing core, the result is one of the most powerful explosions in the entire universe. Supernova. For a brief moment, a single supernova explosion can release more energy than the Sun will produce during its entire lifetime. The explosion blasts the outer layers of the star across space at millions of kilometers per hour. These explosions are so bright that they can briefly outshine entire galaxies. But deep inside the wreckage of that exploding star, something even stranger may form. If the remaining core of the star is smaller, denser, more extreme, eventually the mass of the star becomes compressed into an unbelievably tiny region of space. At that point, gravity becomes so powerful that the escape velocity exceeds the speed of light. And when even light cannot escape, the star disappears. A black hole is born. But the story of black holes does not begin with exploding stars. In fact, the idea of black holes was first imagined more than 200 years ago, long before modern astronomy existed. In 1783, An English scientist named John Michel proposed a strange idea. He wondered what would happen if a star became extremely massive and dense. At the time, scientists believed that light behaved like tiny particles. Michel reasoned that if gravity could pull objects like rocks or cannonballs back to Earth, perhaps it could also pull back particles of light. If a star became massive enough, its gravity might become so strong that light could not escape. Such a star would appear completely dark to outside observers. In other words, it would become invisible. Michel called these hypothetical objects dark stars. It was an astonishingly accurate prediction, but in the 1700s, there was no way to test the idea. More than a century, the concept was mostly forgotten. Then, in the early 20th century, a young physicist changed the way humanity understood gravity forever. His name was Albert Einstein. In 1915, Einstein introduced one of the most revolutionary ideas in the history of science, the theory of general relativity. Before Einstein, scientists believed gravity was simply a force pulling objects toward one another. But Einstein proposed something much stranger. He suggested that gravity is actually the bending of space and time itself. They warp space so dramatically that all possible paths lead inward. Even light cannot escape. Ironically, Einstein himself doubted that such extreme objects could actually exist in nature. He believed the universe would somehow prevent a star from collapsing that much. But the universe turned out to be far stranger than even Einstein imagined. In the decades that followed, astronomers began discovering evidence that these mysterious objects were real. Today, black holes are not just theoretical ideas. They are an essential part of how the universe works. And some of them are far larger and more powerful than anything scientists once believed possible. Because the black holes formed from dying stars are only There exists another class of black holes so enormous that they sit at the centers of galaxies. These cosmic giants contain the mass of millions or even billions of suns. They control the motion of entire galaxies, including our own. At the center of the Milky Way lies a supermassive black hole known as Sagittarius A star. This monster contains the mass of roughly 4 million suns, and it silently lurks about 26,000 light-years away from Earth. For decades it remained completely invisible, but in 2022, scientists finally captured the first direct image of it. The image revealed the edge of a black hole is known as the event horizon. This boundary marks the exact point where escape becomes impossible. If you were floating in space and slowly approached a black hole, nothing unusual would appear at first. From a distance, a black hole does not behave like some cosmic vacuum cleaner that instantly sucks everything in. In fact, if our sun were magically replaced by a black hole with the same mass, Earth would continue orbiting almost exactly the same way it does now. Gravity at a distance behaves normally, but as you move closer to a black hole, something extraordinary begins to happen. The gravity grows stronger and stronger. Not just stronger in the ordinary sense, but uneven. This difference in gravitational pull is known as tidal force. Near Earth, tidal forces cause the oceans to rise and fall, creating the tides. But near a black hole, tidal forces become unimaginably powerful. The closer you move toward the event horizon, the greater the difference in gravitational pull between your feet and your head. Eventually, this difference becomes so extreme that your body would begin to disintegrate. Stretch. Your feet would be pulled much harder than your head. You would slowly be stretched longer and thinner. Scientists have given this horrifying process a surprisingly simple name. They call it spaghettification. The black hole literally stretches objects into long strands of matter, like spaghetti. Any spacecraft approaching too closely would suffer the same fate. Metal would bend and tear. Structures would snap. Atoms themselves could eventually be pulled apart. But strangely, if the black hole is extremely large, such as a supermassive black hole, the tidal forces at the event horizon might actually be relatively gentle. In theory, an astronaut crossing the event horizon of a supermassive black hole might not fool anything unusual at the exact moment of crossing. There would be no wall, no sudden shock, no visible boundary. In space where escape is no longer possible. From that moment onward, every possible path through space and time leads deeper into the black hole. Even light itself would be trapped. But something even stranger would happen if someone were watching the astronaut from far away. From the astronaut's perspective, they would cross the event horizon normally. But from the perspective of a distant observer, something bizarre occurs. As the astronaut approaches the event horizon, time appears to slow down. The astronaut's movements become slower and slower. Signals from the astronaut take longer and longer to reach the observer. Eventually, the astronaut appears to freeze in place right at the edge of the black hole. Their image becomes dimmer and dimmer as the light they emit loses energy while climbing out of the intense gravitational field. To the distant observer, the astronaut never actually crosses the event. They simply fade away. This strange effect is called gravitational time dilation. According to Einstein's theory of general relativity, gravity affects the flow of time itself. The stronger the gravitational field, the slower time moves. Near the surface of Earth, this effect is extremely tiny, but near a black hole, the effect becomes dramatic. Time near the event horizon slows almost to a stop compared to the rest of the universe. This leads to one of the most fascinating possibilities predicted by physics. In theory, if someone could orbit extremely close to a black hole and then return to Earth, they might find that many years had passed outside, while only a short time passed for them. In other words, black holes could act as natural time machines to the future. But once someone crosses the event horizon, there is no turning back. Inside the black hole, the structure of space and time becomes completely warped. All possible directions lead toward the singularity at the center. The singularity is perhaps the strangest concept in all of physics. It represents a point where density becomes infinite and the curvature of space-time becomes infinite as well. Our current understanding of physics simply cannot describe what happens there. The equations break down. General relativity predicts the singularity, but it cannot explain its true nature. To understand what happens inside a black hole, scientists believe we need a theory that combines general relativity with quantum mechanics. Such a theory is often referred to as quantum gravity. For decades, physicists have been searching for this theory. Some believe the answer may lie in string theory. Others explore ideas such as loop quantum gravity. But so far, the true nature of what happens inside remains elusive. Nature of singularities remains one of the greatest unsolved mysteries in science. Despite this mystery, black holes are not completely hidden from observation. Even though the black hole itself is invisible, its influence on nearby matter can reveal its presence. One of the most dramatic phenomena caused by black holes occurs when they interact with nearby stars. If a star passes too close to a black hole, the tidal forces can tear the star apart. In a catastrophic event known as a tidal disruption event, the star is literally shredded by gravity. Its gas is stretched into long streams that spiral toward the black hole. As the material falls inward, it forms an accretion disk, a rapidly spinning ring of superheated gas. Temperatures inside the disk can reach millions of degrees. The glowing gas emits enormous amounts of radiation, including X-rays and gamma rays. A dying star can produce a flare of light visible across millions of light years. Astronomers have observed several of these cosmic feeding events. Each one reveals just how destructive black holes can be. But not all black holes feed so violently. Many black holes spend most of their time relatively quiet, simply drifting through space. Some wander alone through the galaxy, after being kicked away from their birthplaces by supernova explosions. Others sit at the centers of galaxies, quietly influencing the motion of billions of stars. And some black holes grow to sizes that are almost impossible to comprehend. At the heart of most galaxies lies a supermassive black hole. These giants can contain the mass of millions or even billions of suns. Our own galaxy, the Milky Way, is no exception. At its center lies a supermassive black hole called Sagittarius A star. For decades, astronomers could not see it directly, but they noticed something strange about the stars near the center of the galaxy. These stars were moving incredibly fast. Some completed their orbits in just a few years. The only way to explain such motion was if a massive invisible object was pulling them inward. By tracking the motion of these stars, scientists calculated the mass of the hidden object. The result was astonishing. The object contained the mass of roughly 4 million suns, yet it occupied a region smaller than our solar system. Only a black hole could explain such an extreme concentration of mass. In 2022, the Event Horizon Telescope project achieved a historic breakthrough. Using a network of radio telescopes spread across the Earth, scientists created a telescope as large as our entire planet. This allowed them to capture the first direct image of Sagittarius A star, ring of gas surrounding a dark central shadow. That shadow marked the location of the black hole's event horizon. For the first time in human history, we had actually seen the edge of a black hole. But Sagittarius A star is small compared to some of the monsters that exist elsewhere in the universe. Some supermassive black holes contain billions of times the mass of our Sun. The black hole at the center of galaxy Messier 87, for example, has a mass about 6.5 billion times greater than the Sun. Its event horizon is larger than our entire solar system. And yet, even these giants may not be the largest black holes in existence. Astronomers have discovered a category known as ultramassive black holes, which may contain tens of billions of solar mass. These colossal objects dominate the centers of the largest galaxies. Their gravitational influence shapes the structure of entire galaxy clusters. But perhaps the most surprising discovery about black holes is that they are not completely black. In 1974, physicist Stephen Hawking made a groundbreaking discovery. Using quantum mechanics, Hawking showed that black holes should actually emit a tiny amount of radiation. This phenomenon is now known as Hawking radiation. According to quantum physics, empty space is not truly empty. Tiny pairs of particles constantly appear and disappear in what is known as quantum fluctuation. Normally, these particle pairs annihilate each other almost instantly. But near the event horizon of a black hole, something unusual can happen. One particle may fall into the black hole, while the other escapes. To an outside observer, it appears as if the black hole is emitting particles. Over incredibly long periods of time, this process causes the black hole to slowly lose mass. Eventually, after trillions upon trillions of years, the black hole could evaporate completely. This discovery led to one of the most famous puzzles in modern physics, the black hole information paradox. If a black hole eventually evaporates, what happens to the information contained in everything that fell into it? According to quantum mechanics, information can never be destroyed. But if a black hole disappears, where does that information go? This question has puzzled physicists for decades. Some theories suggest that the information may be encoded on the event horizon itself. Others propose that black holes may connect to other regions of the universe through structures known as wormholes. Although many of these ideas remain speculative, they highlight just how deeply black holes challenge our understanding of reality. Black holes are not simply cosmic monsters, laboratories for the most extreme physics imaginable. They push gravity, quantum mechanics, and the structure of space-time to their limits. By studying them, scientists hope to uncover the fundamental laws that govern the universe. And yet, even with all we have learned, black holes remain deeply mysterious, because the closer we look, the stranger they become. And the next mystery is perhaps the most fascinating of all. What would actually happen if you fell into a black hole? The answer is far more bizarre than most people imagine, and it begins with a journey toward the moon. If you were drifting through space and slowly approaching a black hole, the universe around you would begin to behave in very strange ways. At first, nothing dramatic would happen. From far away, a black hole is simply another massive object in space. You would feel its gravity, just as you feel the gravity of a star or a planet. But as you moved closer, the effects of gravity would begin to intensify. Stars behind the black hole would appear distorted. Their light would bend as it passed through the curved space surrounding the black hole. This bending of light is known as gravitational lensing. The black hole would act like a cosmic magnifying glass, warping and twisting the images of objects behind. Instead of seeing a simple dark sphere, you might see a glowing ring of distorted starlight surrounding the black hole. This ring is called the photon sphere. It represents a region where light itself can orbit the black hole. Imagine that. Light, which normally travels in straight lines across the universe, can actually circle a black hole like a satellite orbiting a planet. But these orbits are extremely unstable. Any tiny disturbance would cause the light either to escape outward or spiral inward past the event horizon. As you continued approaching the black hole, the sky behind you would begin to change dramatically. Because gravity bends light, the black hole would begin to pull the entire universe into a strange, distorted view around it. Light from behind you would be curved forward. Eventually, you could see stars that were actually located behind your head, appearing in front of you. The entire sky would seem to wrap around the black hole. Space itself would look twisted. But the most dramatic change would not be what you see. It would be what happens to time. According to Einstein's theory of general relativity, gravity affects the passage of time. The stronger the gravitational field, the slower time flows. Near the surface of Earth, this effect is extremely small. In fact, scientists have measured it using very precise atomic clocks. Clocks placed at higher altitudes tick slightly faster than clocks closer to Earth's surface, because gravity is weaker farther away from the planet. But near a black hole, this effect becomes incredibly powerful. As you approach the event horizon, time for you would begin to slow down relative to the rest of the universe. To you, everything would feel normal. Your heartbeat would remain steady. Your thoughts would flow at their usual pace. But to someone observing you from far away, your movements would appear slower and slower. If you tried to send a signal back to your friends, watching from a distant spacecraft, the signals would take longer and longer to reach them. Eventually, from their perspective, your signals would stop arriving altogether. They would see you frozen at the edge of the event horizon. But from your perspective, you would continue drifting inward. You would cross the event horizon without noticing any visible boundary. And once you crossed it, your fate would be sealed. Inside the event horizon, the rules of space and time change completely. Outside a black hole, you can move in any direction you choose. Choose forward, backward, left, right. But inside the event horizon, all directions lead toward the center. The singularity becomes part of your future, just as tomorrow is part of your future right now. No matter how hard you tried to escape, you could never move away from the singularity. It would be as impossible as trying to travel backward in time. As you fell deeper into the black hole, the tidal forces would become increasingly powerful. The difference in gravitational pull between your feet and your head would grow stronger and stronger. At some point, this difference would stretch your body into a long, thin shape. Your bones would break. Your organs would be pulled apart. Eventually, even the molecules in your body would separate. Finally, the atoms themselves would be torn apart by the immense gravitational forces. This is the ultimate fate of anything that falls into a black hole. But the story may not end there, because when physicists try to understand what happens at the singularity, they encounter one of the greatest mysteries in science. Our current theories simply cannot describe it. General relativity predicts that the singularity is a point of infinite density, but infinities in physics usually indicate that a theory has reached its limit. They signal that something deeper is missing from our understanding. This is why scientists believe that black holes may hold the key to a deeper theory of the universe, a theory that unites gravity with quantum mechanics. Some physicists believe that the singularity might not actually be infinitely small. Instead, quantum effects might prevent matter from collapsing completely. The core of a black hole might be some exotic state of matter that we have not yet discovered. Others have proposed even stranger possibilities. Some theories suggest that black holes might connect to other regions of space through tunnels known as wormholes. A wormhole is a hypothetical shortcut through space-time. Imagine folding a sheet of paper so that two distant points touch each other. A wormhole would act like a tunnel connecting those 2 points. In theory, a wormhole could allow travel between distant parts of the universe almost instantly. However, most physicists believe that wormholes would be extremely unstable. They would collapse almost instantly after forming. Still, the mathematics of general relativity allows them to exist, and black holes remain one of the few places in the universe where such extreme structures might form. Another fascinating possibility is that black holes may give birth to entirely new universes. Some cosmologists have suggested that the singularity inside a black hole might expand into a new region of space-time. On the outside, we would see a black hole, but on the inside, it might be the beginning of another universe. If this idea is correct, our own universe might even have been born from a black hole inside another universe. This idea remains highly speculative, but it shows just how mysterious black holes truly are. They may not just destroy matter, they might create entirely new cosmic realities. Despite their terrifying nature, black holes also play an important role in shaping the universe. They help regulate the growth of galaxies. They influence the motion of stars. They may even help trigger the formation of new stars by compressing clouds of gas. Far from being simple cosmic destroyers, black holes are deeply connected to the structure and evolution of the universe itself. And yet many mysteries remain. How did the enormous black holes at the centers of galaxies grow so large? Did they form from the collapse of giant stars? Or were they born during the earliest moments after the Big Bang? Some astronomers believe that the first black holes formed when the earliest stars in the universe exploded as supernovae. These early black holes may have merged together over billions of years, gradually growing into the supermassive giants we observe today. Others suggest that enormous clouds of gas in the early universe may have collapsed directly into black holes without forming stars first. These so-called direct collapse black holes could have started out already millions of times more massive than the Sun. The true answer remains one of the biggest questions in astrophysics. As telescopes become more powerful and new instruments are developed, scientists hope to observe the earliest black holes forming in the young universe. Such observations could reveal how these cosmic giants were born. Reveal something even more surprising. Because every time we study black holes more closely, the universe reveals something new. Something unexpected. Something that challenges everything we thought we knew. Black holes are not just objects in space. They are gateways to understanding the deepest laws of reality. They force us to question our assumptions about time, space, matter, and information. And as we continue exploring the cosmos, they may lead us toward discoveries that completely transform our understanding of the universe. But black holes are not the only extreme objects in the cosmos. There are stars so dense that a single teaspoon of their material would weigh billions of tons. There are explosions so powerful they can briefly outshine entire galaxies. And there are cosmic events where black holes collide with each other, sending ripples through the fabric of space itself. These ripples are known as strong gravitational waves, and their discovery opened an entirely new way of observing the universe. Because when two black holes collide, the universe itself begins to ring like a giant cosmic bell. And those ripples carry secrets from some of the most violent events ever to occur. Events that can shake the very structure of space and time. And the discovery of those ripples would eventually confirm one of Einstein's most extraordinary predictions. One of the most extraordinary discoveries about black holes came from something that seemed impossible to detect. For decades, scientists believed that if two black holes collided with each other, the event would be completely invisible. After all, black holes do not emit light. They swallow it. So if two of them merged in the depths of space, how could anyone ever know? The answer came from a prediction made by Albert Einstein more than 100 years ago. According to Einstein's theory of general relativity, massive objects do not simply exist in space. They actually warp the fabric of space-time around them. And when massive objects move or accelerate, they create ripples in this fabric. These ripples are known as gravitational waves. Imagine dropping a stone into a calm lake. The water surface forms waves that spread outward in all directions. In a similar way, when massive objects move through space-time, they generate waves that travel across the universe. But these waves are incredibly tiny. By the time they reach Earth, they distort space by less than the width of a single atomic nucleus. Detecting such tiny distortions seemed almost impossible. Yet in 2015, scientists finally succeeded. A pair of enormous detectors called LIGO, located in the United States, measured the first gravitational waves ever observed. The signal came from two black holes that had collided 1.3 billion light-years away. Those black holes was about 30 times the mass of our Sun. For millions of years, they had been orbiting each other, slowly spiraling closer and closer. As they approached each other, they began spinning faster and faster. Eventually, they collided and merged into a single larger black hole. The collision released an unimaginable amount of energy. In just a fraction of a second, the merging black holes converted about 3 times the mass of our Sun into pure energy. That energy rippled through space-time as gravitational waves. After traveling across the universe for more than 1 billion years, those waves finally reached Earth. And for the first time in human history, scientists were able to measure them. The discovery confirmed one of Einstein's most remarkable predictions, but more importantly, it opened an entirely new way of observing the universe. Traditional telescopes rely on light. Gravitational wave detectors allow scientists to observe events that produce no light at all. This means we can now detect black hole collisions that would otherwise remain completely invisible. Since that first discovery, scientists have detected dozens of black hole mergers. Each event provides new information about how black holes form and evolve. Some of these collisions involve black holes that are surprisingly massive. Others involve objects that challenge our understanding of how black holes are created. Each detection helps astronomers build a clearer picture of the hidden universe. And the universe appears to be full of these violent collisions. Across the cosmos, black holes are constantly forming, growing, and merging. But black holes are not always solitary monsters drifting through space. Many exist in pairs. These are known as binary black holes systems. In such systems, two black holes orbit each other, just like two stars might. Their dance can last millions or even billions of years. Slowly, they lose energy through gravitational waves. As they lose energy, their orbit shrinks. They spiral closer and closer together. Eventually, their speed becomes astonishing. In the final moments before merging, the black holes may orbit each other hundreds of times per second. Then, in a final violent moment, they collide and combine into a single larger black hole. The energy released in that instant can briefly exceed the brightness of all the stars in the observable universe combined. Yet the event produces no visible light. Only gravitational waves carry the news of the collision across space. But perhaps the most fascinating black holes of all are the ones that sit quietly at the centers of galaxies. Appears to contain a supermassive black hole at its core. These giants contain millions or billions of times the mass of our Sun. Their influence extends across entire galaxies. For a long time, astronomers wondered whether these supermassive black holes formed after galaxies formed, or whether they helped galaxies form in the first place. Today, many scientists believe that the growth of galaxies and the growth of their central black holes are closely connected. When matter falls into a supermassive black hole, enormous amounts of energy can be released. This energy can produce powerful jets of radiation that shoot out from the galaxy's center at nearly the speed of light. These jets can extend for thousands of light years. They can heat surrounding gas and even stop new stars from forming. In this way, black holes may act as regulators that control how galaxies grow. Without them, galaxies might grow far larger, more chaotic than they are today. In other words, black holes may actually help maintain the structure of the universe. But despite their enormous power, black holes are not eternal. In 1974, physicist Stephen Hawking made a discovery that shocked the scientific world. Using the laws of quantum mechanics, Hawking showed that black holes should slowly lose energy over time. This process occurs because of quantum fluctuations near the event horizon. In quantum physics, empty space is never truly empty. Pairs of tiny particles constantly appear and disappear. Normally, these particle pairs annihilate each other almost instantly. But near a black hole's event horizon, one particle may fall into the black hole while the other escapes. To an outside observer, it appears as if the black hole is emitting radiation. This radiation is now known as Hawking radiation. Over extremely long periods of time, this radiation causes the black hole to slowly lose mass. The smaller the black hole becomes, the faster it loses energy. Eventually, after unimaginable lengths of time, the black hole may evaporate completely. For stellar mass black holes, this process would take far longer than the current age of the universe. But theoretically, every black hole will eventually disappear. This leads to one of the deepest puzzles in modern physics. If a black hole eventually evaporates, what happens to everything that fell into it? Does the information about those objects disappear forever? According to the laws of quantum mechanics, information can never truly be destroyed. But if a black hole evaporates completely, where does that information go? This question is known as the black hole information paradox. For decades it has challenged physicists, trying to reconcile quantum mechanics with general relativity. Scientists believe that the information may somehow be stored on the surface of the event horizon. Others believe it may escape slowly through Hawking radiation. And some propose that the information might be preserved in ways we do not yet understand. Solving this paradox could lead to a revolutionary new theory of physics, a theory that unites the large-scale world of gravity with the microscopic world of quantum particles. And black holes may be the key to discovering that theory, because nowhere else in the universe do these two realms collide so dramatically. Black holes push gravity to its extreme limits. They compress matter beyond anything we can reproduce on Earth. They stretch space and slow time in ways that challenge our deepest assumptions about reality. They are both destroyers and creators. They swallow stars, shape galaxies, and send gravitational waves rippling across the cosmos. The deeper we study them, the more mysterious they become. Every answer leads to new questions. Every discovery reveals deeper layers of complexity. Black holes remind us that the universe is far stranger than our everyday experiences suggest. They show us that reality is not always intuitive. Time can slow, space can bend, light itself can be trapped, and somewhere beyond the event horizon of every black hole lies a region of spacetime that we still cannot fully understand, a place where the known laws of physics collapse, a place that may hold the key to the deepest secrets of the universe. But black holes are only one part of an even larger cosmic story. Because some black holes are so enormous that they control the evolution of entire galaxies, these are the supermassive black holes, and understanding how these giants formed may reveal how the universe itself evolved after the Big Bang. The story of those cosmic giants is even more astonishing than the birth of black holes from dying stars, because some of them appeared surprising. In the beginning, the universe was a very different place. Shortly after the Big Bang, there were no stars, no planets, and no galaxies. The universe was filled mostly with hydrogen and helium gas, slowly cooling as space expanded. For hundreds of millions of years, the cosmos remained dark. This period is often called the cosmic dark ages. There were no stars shining in the sky, no galaxies lighting up the universe, just enormous clouds of gas drifting through the expanding darkness. But gravity was already at work. Over time, small variations in density began to grow. Regions with slightly more gas began pulling in more matter from their surroundings. Slowly, enormous clouds of hydrogen began collapsing under their own gravity. Inside these clouds, the first stars were born. These first-generation stars are known as population 3 stars. From the stars we see today. Because the early universe contained almost no heavy element, these stars were composed almost entirely of hydrogen and helium. Without heavier elements to cool the collapsing gas clouds, these early stars grew incredibly large. Some may have been hundreds of times more massive than our sun. They burned extremely hot and extremely fast. While our sun will live for about 10 billion years, many of these giant stars may have lived only a few million years. Their lives were brief but spectacular. Inside their cores, nuclear fusion created the first heavy elements in the universe: carbon, oxygen, iron. These elements would later become the building blocks of planets and life itself. But when these enormous stars died, their deaths were just as dramatic as their lives. Many of them exploded as powerful supernovae. Others may have collapsed directly into black holes. These early black holes could have been much larger than those formed by stars today. And because they formed so early in the universe, they had billions of years to grow. Over time, these early black holes may have merged with others. They may have consumed huge amounts of gas. Slowly, they could have grown into the supermassive black holes we see at the centers of galaxies today. But there is a problem with this explanation. Some supermassive black holes appear to have formed incredibly quickly. Astronomers have observed quasars, extremely bright objects powered by black holes, that existed less than 1 billion years after the Big Bang. These quasars contain black holes with masses of billions of suns. Growing such enormous black holes in such a short time is extremely difficult to explain. Even if a black hole continuously consumed matter at the fastest possible rate, might still not grow quickly enough to reach such enormous size. This mystery has led scientists to explore alternative ideas. One possibility is that some black holes formed directly from enormous clouds of gas in the early universe. Instead of forming stars first, these clouds may have collapsed directly into black holes containing hundreds of thousands of solar masses. These objects are known as direct collapse black holes. Starting from such a large mass would make it much easier for them to grow into the supermassive giants we observe today. Another possibility is that the early universe produced unusual stars far larger than any that exist today. These stars could have collapsed into massive black holes shortly after forming. Over billions of years, repeated mergers between black holes could have created the enormous objects at the centers of galaxies. Uncertain, but new telescopes are beginning to reveal clues. In 2022, the James Webb Space Telescope began observing some of the most distant objects ever seen. Its powerful instruments can peer back in time to when the universe was only a few 100 million years old. Already, astronomers have discovered galaxies and black holes that appear to be far larger and more developed than expected for such an early period in cosmic history. These discoveries suggest that the early universe may have been far more active and complex than scientists once believed. Black holes may have formed and grown faster than our current theories predict. As new observations continue, we may soon learn how these cosmic giants truly formed. But black holes are not only fascinating because of their origins. They also produce some of the most powerful phenomena in the universe. When matter falls toward a black hole, it rarely disappears quietly. Instead, it forms an accretion disk, a rapidly spinning ring of gas and dust. Inside this disk, friction between particles generates enormous heat. Temperatures can reach millions of degrees. The glowing gas produces intense radiation across the electromagnetic spectrum. Sometimes the energy released near a black hole can power enormous jets of particles. These jets shoot outward from the poles of the black hole at speeds close to the speed of light. They can stretch across thousands or even millions of light years. Some of these jets are so powerful that they influence the entire galaxy surrounding the black hole. They can heat interstellar gas, preventing it from collapsing into new stars. In this way, black holes may control how galaxies evolve over billions of years. One of the most dramatic examples of this phenomenon occurs in galaxies known as quasars. Quasars are among the brightest objects in the entire universe. They are powered by supermassive black holes consuming enormous amounts of matter. The light from a quasar can outshine all the stars in its host galaxy combined. Some quasars are so distant that their light has been traveling toward us for more than 12 billion years. When we observe them, we are seeing the universe as it existed shortly after the first galaxies formed. Studying these objects helps astronomers understand how black holes and galaxies evolved together over cosmic time. Despite their immense power, black holes do not always remain active. Once a black hole consumes most of the nearby gas and dust, it can become quiet again. Many supermassive black holes spend long periods in a dormant state. They still exist at the centers of galaxies, but they are no longer actively feeding. Whole, Sagittarius A star, is currently in such a quiet phase. It occasionally consumes small amounts of gas or dust, producing brief flares of radiation. But compared with the blazing activity of quasars, it is relatively calm. However, this peaceful state may not last forever. If a large cloud of gas or an unlucky star drifts too close to Sagittarius A star, the black hole could awaken again. The result could be a burst of radiation powerful enough to illuminate the center of the Milky Way. Fortunately for Earth, we are located far from the galactic center, about 26,000 light-years away. At that distance, even a major outburst from our galaxy's black hole would likely have little effect on our planet. But black holes can still influence their surroundings in surprising ways. For example, when two galaxies collide and merge, their central black holes may eventually meet. Over millions of years, the black holes spiral toward each other. Eventually, they collide and merge into a single larger black hole. These events release enormous bursts of gravitational waves. In the distant future, astronomers hope to detect such collisions between supermassive black holes using space-based gravitational wave detectors. Observing these events could reveal how galaxies grow and merge over cosmic time. The universe is constantly evolving. Stars are born, stars die, galaxies collide, black holes grow. Every event is part of a vast cosmic story stretching across billions of years, and black holes occupy some of the most important chapters in that story. They represent the ultimate limits of gravity. They challenge our understanding of physics. They push space and time to their breaking point. And yet, despite everything we have learned, black holes remain deeply mysterious. What truly happens at the singularity? Is information preserved or destroyed? Could black holes connect to other universes? Or might they reveal entirely new laws of physics that we have not yet discovered? These questions remain unanswered. But one thing is certain. Black holes are not just strange objects hidden in distant galaxies. They are keys to understanding the deepest structure of the universe. And as scientists continue to explore the cosmos, black holes will remain at the center of some of the most exciting discoveries yet to come. Because the closer we look into the darkness of a black hole, the more the universe reveals about itself, and the more we realize how much there is still left to discover. Black holes force us to confront some of the most extreme conditions that can exist anywhere in the universe. They are places where gravity becomes so powerful that it reshapes the very fabric of reality. Space bends, time slows, light itself becomes trapped. And yet, for all their power, black holes are surprisingly simple objects. According to classical physics, a black hole can be completely described by just three properties: mass, spin, and electric charge. This idea is known as the no-hair theorem. The theorem suggests that once matter falls into a black hole, all of its complex properties disappear. The black hole retains only the total mass, the rotation, and the electric charge of everything that has fallen inside. Everything else is lost. A star, a planet, a cloud of gas, or even an entire civilization falling into a black hole would all end up contributing only their mass and angular momentum. All other information would appear to vanish. This idea deeply troubled many physicists, because according to the laws of quantum mechanics, information should never be destroyed. In quantum theory, every particle carries information about its state. Even if the particle changes form or interacts with others, that information must still exist somewhere in the universe. If black holes truly erased information, it would mean that one of the most fundamental principles of physics was wrong. This conflict led to one of the greatest debates in modern science, the black hole information paradox. For decades, physicists struggled to find a solution. Some believed that information truly was lost forever inside black holes. Others argued that the laws of quantum mechanics must somehow preserve it. The debate continued for years, with no clear answer. Then, in the 1990s, new ideas began to emerge. One of the most fascinating proposals came from theoretical physics known as the holographic principle. This idea suggests that the information contained inside a volume of space may actually be encoded on its boundary. In other words, the entire three-dimensional contents of a region could be represented by information stored on a two-dimensional surface. For black holes, this would mean that information about everything that falls inside might be stored on the event horizon itself. The surface of the black hole could act like a kind of cosmic storage device, a holographic record of everything that has ever entered. Although the details are still being studied, this idea has gained strong support among physicists. It suggests that information is not destroyed by black holes after all. Instead, it may be preserved in ways that are extremely difficult to detect. But black holes may hide even more astonishing possibilities. Some theories propose that black holes might be connected to objects known as white holes. A white hole is essentially the opposite of a black hole. While a black hole pulls matter inward, a white hole would push matter outward. Nothing could enter a white hole from the outside. Matter and energy could only emerge from it. Although white holes have never been observed, they appear as mathematical solutions to Einstein's equation. Some scientists speculate that a black hole might be connected to a white hole through a tunnel in space-time. This tunnel would be what we call a wormhole. A wormhole could theoretically connect two distant regions of space, or even two different universes. If such structures exist, they might allow matter to travel enormous distances almost instantly. However, there are serious challenges with this idea. Most calculations suggest that wormholes would be extremely unstable. They would collapse almost immediately unless held open by exotic forms of matter that we have never observed. For now, wormholes remain a fascinating possibility rather than a confirmed reality. Study of black holes continues to reveal surprising insights. They are not simply cosmic monsters that swallow everything in their path. They are also engines of creation. The explosions that produce black holes, supernova, scatter heavy elements throughout the universe. Those elements eventually form new stars, planets, and even life. The iron in your blood and the calcium in your bones were forged inside ancient stars that exploded billions of years ago. Some of those explosions may have created black holes. In this way, black holes are indirectly connected to the very existence of life. They are part of the cosmic cycle of birth, destruction, and renewal that shapes the universe. But the mysteries of black holes extend even further. Some physicists believe that studying black holes could lead to the discovery of a unified theory of physics. Today, our understanding of the universe is based on two major theories. General relativity describes gravity and the large-scale structure of the cosmos. Quantum mechanics describes the behavior of particles at the smallest scales. Both theories are extremely successful in their own domains, but they are fundamentally incompatible with each other. When scientists try to combine them under extreme conditions, such as those inside a black hole, the equations break down. This suggests that a deeper theory must exist, a theory that unites gravity with quantum physics. Black holes may provide the clues needed to discover that theory, because nowhere else in the universe do these two realms interact so dramatically. The intense gravity of black holes compresses matter to extremely small scales, where quantum effects become important. By studying black holes, physicists hope to understand how gravity behaves at the quantum level. Solving this puzzle could transform our understanding of the universe. It could reveal the true structure of space and time. It could explain the nature of dark matter and dark energy. It could even reveal what happened at the very beginning of the universe. In this sense, black holes are not just mysterious objects. They are gateways to deeper knowledge. They push the boundaries of what we know, and they challenge us to rethink our assumptions about reality. Over the past century, our understanding of black holes has grown enormously. What once seemed like a strange theoretical idea has become a central part of modern astrophysics. We have observed stars orbiting invisible black holes. We have detected gravitational waves from black hole collisions. We have photographed the shadows of supermassive black holes. Each discovery has brought us closer to understanding these cosmic giants. Ahead, new observatories are being built. More powerful telescopes are being launched into space. Future gravitational wave detectors will be able to detect collisions between supermassive black holes across the universe. These instruments will allow scientists to explore black holes with unprecedented detail. They may reveal how the first black holes formed. They may uncover the physics of the event horizon. They may even provide hints about what lies beyond the singularity. The coming decades may revolutionize our understanding of black holes. But even as we learn more, the sense of mystery remains. Black holes remind us that the universe is far stranger than our everyday experience suggests. They show us that time can slow, space can stretch, and gravity can become so powerful that it tramps light itself. They are reminders that the cosmos still holds countless secrets waiting to be discovered. And perhaps the most exciting truth is this: every time humanity looks deeper into the universe, we discover that reality is even more extraordinary than we imagined. Black holes are not just objects in space. They are symbols of the unknown, and exploring them is part of humanity's endless quest to understand the universe we inhabit. Because somewhere in the darkness of a black hole, the next great discovery may already be waiting. One of the most historic moments in the study of black holes happened in April of 2019. For the first time in human history, scientists managed to capture an image of a black hole. For decades, black holes had only existed in theory and indirect observation. Astronomers had detected the radiation produced by material falling into them, and they had observed stars orbiting invisible objects with enormous mass. All the evidence pointed to the existence of black holes, but no one had ever actually seen one. The challenge was enormous. Black holes are extremely distant, and their event horizons are relatively small compared to the vast scales of space. Trying to photograph a black hole is often compared to trying to photograph a donut on the surface of the moon while standing on Earth. To accomplish this task, scientists created an extraordinary global project known as the Event Horizon Telescope. Instead of building one giant telescope, they connected radio telescopes across the entire planet. Observatories in North America, South America, Europe, Antarctica, and Hawaii were all linked together. By synchronizing these telescopes with extremely precise atomic clocks, scientists effectively created a virtual telescope the size of the Earth itself. This technique is called very long baseline interferometry. The combined system had the resolution necessary to observe the shadow of a black hole. In April 2017, the telescopes began collecting data. Petabytes of information were recorded and stored on specialized hard drives. The amount of data was so large that it had to be physically transported to supercomputers for processing. For 2 years, scientists worked to analyze and reconstruct the data. Finally, in 2019, the world saw the result: a glowing orange ring surrounding a dark center. That dark region was the shadow of a black hole. The black hole photographed was located in the center of a galaxy called Messier 87, about 55 million light-years from Earth. This object, known as M87 star, is truly enormous. It contains about 6.5 billion times the mass of our Sun. Its event horizon is larger than our entire solar system. The glowing ring seen in the image is formed by superheated gas orbiting the black hole at incredible speeds. This gas reaches temperatures of billions of degrees and emits powerful radiation as it spirals inward. But the most important feature of the image is the dark center. That shadow represents the event horizon, the boundary beyond which nothing can escape. Seeing this image confirmed predictions made by Einstein's theory of general relativity more than a century earlier. The shape of the shadow matched the theoretical models almost perfectly. It was a stunning victory for modern physics. But the story did not end there. In 2022, scientists revealed another extraordinary image. This time, the black hole photographed was much closer to home. It was the supermassive black hole at the center of our own galaxy, Sagittarius A star. Unlike the enormous black hole in Messier 87, star is much smaller. It contains about 4 million times the mass of the Sun. Even though it is much closer to Earth, photographing it was actually more difficult. Gas near Sagittarius A star moves extremely rapidly, changing its appearance from minute to minute. This made it harder for scientists to produce a stable image. After years of analysis, they succeeded. The result was another glowing ring surrounding a dark shadow, the silhouette of our galaxy's central black hole. These images represent one of humanity's greatest scientific achievements. For the first time, we were able to directly observe one of the most extreme objects in existence. But black holes are far more than just strange objects hidden in distant galaxies. They are laboratories where the laws of physics are pushed to their limits. They reveal the power of gravity in its most extreme form. It can bend and twist. They demonstrate how matter behaves under unimaginable conditions. And they continue to challenge our understanding of the universe. Because despite everything we have learned, the most important questions remain unanswered. What truly lies inside a black hole? Does the singularity really exist? Is information destroyed when something falls inside? Or does it somehow survive in ways we do not yet understand? Some physicists believe that the event horizon itself may store information about everything that has ever fallen into the black hole. Others suggest that information may escape slowly through Hawking radiation, and some propose that black holes may connect to entirely new regions of space-time, possibly even other universes. These ideas remain speculative, but they demonstrate just how mysterious black holes still are. They sit at the boundary between what we understand and what we do not. That boundary is where some of the most exciting discoveries in science are made. Because every time humanity pushes further into the unknown, we discover that the universe is far stranger than we ever imagined. Black holes were once thought to be impossible. Today we know they exist throughout the cosmos. Tomorrow they may help us uncover the deepest laws of nature. They may reveal how gravity works at the smallest scale. They may help unify the theories of quantum mechanics and relativity. They may even reveal the true nature of space and time. And yet despite all of this, the most terrifying and fascinating question remains: what would actually happen if you fell into one? Not just approaching the event horizon, but crossing it. What would you see? What would you feel? Would you be instantly destroyed? Would time behave differently? Singularity? Or would something even stranger? Physicists have spent decades exploring these questions. Using mathematics, computer simulations, and theoretical models, they have tried to understand what the journey into a black hole might look like. And the results are far more bizarre than anyone expected. Because once you cross the event horizon, the universe begins to behave in ways that seem completely impossible. Time and space begin to swap roles. The future becomes unavoidable. The singularity becomes something you cannot escape. And the deeper you fall, the more reality itself begins to break apart. Even after more than a century of research, black holes continue to challenge the limits of human understanding. They exist at the intersection of the known and the unknown, where the laws of physics stretch to their breaking point. To truly appreciate how strange black holes are, imagine standing on a distant spacecraft and watching a star wander too close to one. At first, the star would simply begin to orbit the black hole, just as planets orbit a star. But the closer the star moved, the stronger the black hole's gravity would become. Eventually, the star would cross a critical boundary known as the tidal radius. At that moment, the black hole's gravity would begin pulling harder on the side of the star closest to it than on the far side. The star would start to stretch. Then the stretching would become extreme. The star would be pulled apart by tidal forces so powerful that the entire star would be torn into long streams of glowing gas. Astronomers call this phenomenon a tidal disruption event. These events release enormous bursts of radiation as the shredded material spirals toward the black hole. For a brief period, the dying star can produce a brilliant flare visible across millions of light years. Telescopes on Earth have detected several such events. Each one provides a rare opportunity to study how black holes interact with their surroundings. These cosmic catastrophes revealed just how destructive black holes can be. But black holes are not only destructive, they are also among the most efficient engines in the universe. When matter falls into a black hole, it can release more energy than almost any other known process. In fact, matter falling into a black hole can convert up to 40% of its mass into energy. For comparison, nuclear fusion inside stars converts less than 1% of mass into energy. This means that black holes can produce extraordinary amounts of power. In some galaxies, supermassive black holes generate jets of particles that travel thousands of light years into space. These jets are accelerated by powerful magnetic fields near the black hole. The particles within them move at nearly the speed of light. When these jets interact with surrounding gas clouds of new stars. In other cases, they can blow gas away from the galaxy's center, preventing new stars from forming. Once again, we see that black holes play a crucial role in shaping the evolution of galaxies. But perhaps the most remarkable discovery about black holes is that they are not completely silent. In the past, astronomers could only study black holes by observing light. But in recent years, scientists have begun listening to the universe in an entirely new way. Through gravitational waves. When two black holes orbit each other, they slowly lose energy by emitting gravitational waves. These waves ripple outward through space-time, carrying information about the motion of the black holes. As the black holes spiral closer together, the waves grow stronger. Their frequency increases. The signal becomes faster and louder. Finally, the two black holes collide. In a fraction of a second, they merge into a single larger black hole. The collision releases a powerful burst of gravitational waves that travel across the universe. These waves stretch and compress space itself as they pass. Detecting these waves requires incredibly sensitive instruments. The detectors must measure distortions in space smaller than the width of an atomic nucleus. This challenge was finally overcome in 2015 when scientists detected the first gravitational wave signal from a pair of merging black holes. It was one of the most important discoveries in modern astronomy. For the first time, humanity had detected ripples in space-time itself. Since then, many more black hole mergers have been detected. Each event provides new information about the population of black holes in the universe. Some of the merging black holes are far more massive than scientists expected. New detection helps astronomers refine their understanding of how black holes form and evolve. But black holes are not limited to the centers of galaxies or the remnants of massive stars. Some scientists believe that tiny black holes may have formed shortly after the Big Bang. These hypothetical objects are known as primordial black holes. During the earliest moments of the universe, small fluctuations in density may have caused certain regions of space to collapse directly into black holes. These primordial black holes could have masses ranging from extremely small to very large. Some might be as small as an asteroid. Others might be thousands of times more massive than the Sun. If they exist, primordial black holes could help explain one of the greatest mysteries in modern cosmology, the nature of dark matter. Dark matter is a mysterious substance that makes up about 85% of the universe's mass. The matter in the universe. It does not emit light, it does not interact with electromagnetic radiation, but its gravitational effects can be seen in the motion of galaxies and galaxy clusters. Some scientists have proposed that a population of primordial black holes might account for at least part of dark matter. Although this idea is still debated, ongoing observations continue to test the possibility. If primordial black holes are ever confirmed, they would provide a remarkable window into the earliest moments of cosmic history. They would reveal how the universe behaved just fractions of a second after the Big Bang, and they would connect black holes directly to the origin of the cosmos itself. But even without primordial black holes, the universe already contains an astonishing number of these objects. Astronomers estimate that the Milky Way alone may contain more than 100 billion black holes. Most of them are invisible. They wander silently through the galaxy, detectable only by their gravitational effect. Some may even be drifting through the empty space between stars. These rogue black holes pose no threat to Earth. The distances between stars are so vast that the chances of one passing close to our solar system are extremely small. But their existence reminds us that the universe is filled with hidden objects that we cannot see directly. The cosmos is far more complex and mysterious than it appears when we look at the night sky. Behind the familiar stars lies an unseen universe of dark matter, neutron stars, and black holes. Each discovery reveals new layers of cosmic complexity, and each new layer raises new questions. Black holes, once thought to be purely theoretical curiosities, have become central to our understanding of the universe. They influence the growth of galaxies. They generate gravitational waves. They challenge our understanding of physics, and they may even hold the key to a deeper theory of reality. Yet the greatest mystery of all still lies beyond the event horizon, because once anything crosses that boundary, it enters a region of space-time that we cannot observe directly. Inside the black hole, the rules of the universe may change in ways we do not yet understand. The singularity may represent a point where our current theories break down, or it may conceal entirely new physics waiting to be discovered. One day, a future theory of quantum gravity may reveal what truly happens there. Until then, the interior of a black hole remains one of the greatest mysteries in science, a place where the known laws of nature reach their limits, a place where the next great breakthrough in physics may be hiding. And perhaps the most extraordinary truth is this: everything we know about black holes has been discovered without ever entering. All our knowledge comes from observing their effects from a safe distance, from the motion of stars, from the glow of accretion, from the faint whispers of gravitational waves. Yet even from afar, black holes have revealed a universe far stranger than anyone once imagined. They have shown us that reality can bend, that time can slow, that space itself can twist into shapes beyond our intuition. And as we continue to explore the cosmos, black holes will remain among the most fascinating objects we study, because within their darkness lies the promise of deeper understanding. They remind us that the universe is not just vast, it is filled with mysteries waiting to be uncovered. And every new discovery brings us one step closer to answering one of the oldest questions humanity has ever asked. Universe truly works? The search for that answer continues. And somewhere, deep within the shadow of a black hole, the next great discovery may already be waiting. Now, imagine something even stranger. Imagine you are floating safely in a spacecraft, millions of kilometers away from a black hole. You are observing another astronaut slowly drifting toward. From your perspective, everything seems normal at first. The astronaut moves closer and closer to the black hole, pulled by its powerful gravity. But as the astronaut approaches the event horizon, something extraordinary begins to happen. Their motion appears to slow down. At first, the change is subtle. Their movements become slightly slower than expected, then slower still. As the astronaut gets closer to the event horizon, the slowing becomes more dramatic. Their movements stretch out in time. Every signal they send takes longer to reach you. Their voice transmission begins to deepen and stretch as the frequency of the signal shifts due to the intense gravitational field. This phenomenon is known as gravitational redshift. Light and radio signals climbing out of a strong gravitational field lose energy. Their wavelength stretches, their color shifts toward the red end of the spectrum. Eventually, the astronaut's signals become so weak and stretched that they disappear completely. From your perspective, the astronaut never actually crosses the event horizon. Instead, they appear to freeze just outside it. Their image becomes dimmer and dimmer until it fades away entirely. To you, it would look as if the astronaut has been permanently suspended at the edge of the black hole. But from the astronaut's own perspective, something very different is happening. Time feels completely normal. Their watch ticks at the usual pace. Their heartbeat remains steady. They continue drifting toward the black hole, and eventually they cross the event horizon. They do not see a wall. They do not feel a sudden jolt. The event horizon is not a physical surface. It is simply a boundary in space-time. Once crossed, escape becomes impossible. Inside the event horizon, the geometry of space-time changes dramatically. You can move in many directions: forward, backward, left, right. You can move closer to the black hole or farther away. But inside the event horizon, the structure of space-time forces everything to move inward. The singularity lies in your future, just as surely as tomorrow lies in your future right now. No matter what direction you try to travel, every path leads toward the center. Even light cannot escape this fate. Inside the black hole, the singularity becomes unavoidable. The closer you fall toward the center, the stronger the tidal forces become. If the black hole is relatively small, such as one formed from a collapsing star, these forces would become extreme very quickly. Your feet would feel a stronger gravitational pull than your head. Your body would begin to stretch. Your spine would elongate. Your bones would crack. Your organs would be pulled apart. Process. Spaghettification would eventually tear your body into a long stream of atoms. But if the black hole were supermassive, the experience could be different. The event horizon of a supermassive black hole can be enormous, sometimes larger than the orbit of Neptune. In such cases, the tidal forces at the event horizon may actually be relatively gentle. An astronaut might cross the event horizon without immediately noticing anything unusual. The stretching forces would become deadly only deeper inside the black hole. But regardless of the black hole's size, the final destination remains the same: the singularity. The singularity is predicted to be a point where density becomes infinite, and space-time curvature becomes infinite as well. At this point, the equations of general relativity break down completely. Physicists believe that quantum effects must become important in such extreme conditions. Complete theory of quantum gravity. We cannot yet describe what truly happens at the singularity. Some theories suggest that the singularity may not actually be infinitely small. Instead, it might be a region where matter exists in a completely new state, governed by quantum physics. Others propose that the interior of a black hole could contain a tunnel leading to another region of spacetime. This idea brings us back to the concept of wormhole. A wormhole is a hypothetical shortcut connecting two distant points in the universe. Imagine folding a piece of paper so that two points touch. A wormhole would act like a tunnel connecting those points. In theory, such a tunnel could allow travel between distant regions of space, almost instantly. Einstein himself explored this possibility in what became known as the Einstein-Rosen bridge. However, most wormhole models are unstable instantly, unless supported by exotic forms of matter that have negative energy. Such matter has never been observed. Still, wormholes remain an intriguing possibility. If they exist, they could revolutionize our understanding of space travel and the structure of the universe. Some scientists even speculate that black holes might connect to white holes, hypothetical objects that expel matter instead of absorbing it. In this scenario, anything that falls into a black hole might eventually emerge from a white hole somewhere else in the universe. Although these ideas remain speculative, they highlight just how mysterious black holes are. They challenge our understanding of reality itself. They force physicists to confront the limits of our theories, and they may hold the key to discovering entirely new laws of nature. But even without these exotic possibilities, black holes are already among the most fascinating objects in existence. They reveal how gravity behaves under extreme conditions. They show how space and time are interconnected. They demonstrate that the universe is far more complex than our everyday experiences suggest. And they remind us that many of the deepest mysteries of the cosmos remain unsolved, because beyond the event horizon lies a region of the universe that we cannot observe directly. A region where the known laws of physics may no longer apply. A region that may contain answers to questions we have not yet even thought to ask. Black holes represent the ultimate frontier of astrophysics. They sit at the edge of knowledge, and every time we study them they reveal something new about the universe, something unexpected, something profound. Because the deeper we explore the cosmos, the more we realize that the universe is far stranger than we ever imagined. And black holes are perhaps the clearest reminder of that truth. They are not simply cosmic curiosities. They are gateways to understanding the deepest workings of reality. And the journey to understand them is only just beginning. H1 Part 2. Falling into a black hole. H1. What would actually happen if you fell into a black hole? It sounds like something from science fiction. A journey into the darkest object in the universe. A place where gravity becomes unstoppable and the laws of physics begin to break down. But physicists have spent decades studying this exact question. Using Einstein's theory of general relativity and modern astrophysics, scientists have been able to predict, at least partially, what such a journey might look like. And the results are stranger than most people expect. Because falling into a black hole would not begin with an explosion, it would begin quietly. Imagine drifting through space in a spacecraft approaching a black hole. At first, the black hole might not even look particularly dramatic. From far away, it would appear as a dark region surrounded by distorted stars. Light from the background universe would bend around it, forming strange warped patterns. This bending of light is caused by gravitational lensing. The black hole's immense gravity curves space itself, forcing light to follow curved path. As a result, the stars behind the black hole would appear stretched and distorted into glowing arcs. Some of the light might even wrap completely around the black hole before reaching your eyes. This means you could see multiple images of the same star at different positions in the sky. The closer you move toward the black hole, the more dramatic this distortion becomes. Eventually, a bright circular ring of light would appear around the black hole. This is known as the photon sphere. Inside this region, gravity is strong enough that light itself can orbit the black hole. Photons, particles of light, can circle the black hole like satellites orbiting a planet. But these orbits are unstable. A slight disturbance will send the photon either escaping into space or falling into the black hole. The photon sphere forms the glowing ring seen in images of black holes captured by telescopes. It is one of the most striking visual features of these cosmic objects. But if you continue approaching the black hole, the most important boundary you will eventually reach is the event horizon. The event horizon is the point of no return. It marks the distance from the black hole where escape velocity becomes greater than the speed of light. Once anything crosses this boundary, it can never escape. Not matter, not energy, not even light. But here is something surprising. The event horizon is not a solid surface. It is not a wall. If you were falling toward it, you would not see any glowing barrier or feel a sudden impact. You would simply drift past an invisible line in space. And once you cross that line, your fate would be sealed. But the experience of crossing the event horizon depends on who is observing. To you, the person falling, seemed normal. Your watch would tick at its usual pace. Your heartbeat would remain steady. Your spacecraft would continue drifting forward. But to someone watching from far away, something bizarre would occur. As you approach the event horizon, your motion would appear to slow down. The closer you get, the slower you would appear to move. Your signals would take longer and longer to reach the distant observer. The light coming from your spacecraft would become stretched and redder as it climbed out of the intense gravitational field. Eventually, from the outside observer's perspective, you would appear to freeze in place at the edge of the black hole. Your image would slowly fade until it disappeared entirely. You would never appear to cross the event horizon. This strange effect happens because gravity affects the flow of time. According to Einstein's theory of general relativity, time moves more slowly in stronger gravitational fields. Near a black hole, this effect becomes extremely powerful. Time near the event horizon slows almost to a stop relative to the rest of the universe. In fact, if you could somehow orbit just outside a black hole's event horizon and then return to Earth, you might discover that many years had passed outside, while only a few hours passed for you. In this way, black holes act as natural time machines to the future, but once you cross the event horizon, time behaves in a very different way. Inside the black hole, space and time effectively swap roles. Outside the black hole, you can move freely in space. You can choose to move closer or farther away. But inside the event horizon, moving away from the center becomes impossible. The singularity lies in your future just as surely as tomorrow lies in your future, right now. No matter what direction you travel, the center, the singularity becomes unavoidable, and as you fall deeper into the black hole, the forces acting on your body begin to grow strong. The difference in gravitational pull between your head and your feet increases. This difference is known as tidal force. Near Earth, tidal forces cause the oceans to rise and fall. But near a black hole, tidal forces become unimaginably powerful. If the black hole is small, perhaps a few times the mass of the sun, these forces would tear you apart long before you reach the event horizon. Your body would stretch into a long, thin shape as your feet were pulled downward faster than your head. This stretching process is known as spaghettification. Eventually, the forces would become so strong that even atoms would be torn apart. But if the black hole were supermassive, millions or billions of times more massive than the sun, could be different. Because the event horizon of a supermassive black hole is extremely large. The tidal forces at the horizon might actually be weak enough that you would not feel anything unusual at the moment of crossing. You could pass through the event horizon without realizing it. Only later, deeper inside the black hole, would the tidal forces become deadly. As you continued falling inward, the curvature of space-time would grow more extreme. Light around you would behave strangely. Photons emitted from your flashlight might curve dramatically as they travel through the warped space around the singularity. Eventually, the singularity would lie ahead. According to classical physics, The singularity is a point where density becomes infinite, but this prediction almost certainly means that our current theory is incomplete. Physicists believe that quantum effects must become important near the singularity. Future theory of quantum gravity may reveal what truly happens. Some theories suggest that the singularity might be replaced by a tiny but finite region where matter exists in an exotic quantum state. Others suggest that the interior of a black hole might connect to another region of spacetime, perhaps even another universe. One idea proposes that black holes could create baby universes. In this scenario, the singularity inside a black hole might expand into a new region of spacetime, forming an entirely new universe. From our perspective, we see a black hole, but inside a new cosmos could be born. Although this idea remains speculative, it highlights just how mysterious black holes are. They sit at the boundary between known physics and unknown physics. They challenge our understanding of space, time, and reality itself. But even without such exotic possibilities, into a black hole remains one of the most extreme experiences imagined, because as you approach the singularity, the forces acting on your body continue to grow. The stretching becomes stronger. The gravitational gradients become more intense. Eventually, the structure of matter itself begins to break apart. And somewhere deep inside the black hole, the journey would come to an end, at least according to our current understanding of physics. But the story of black holes does not end there, because the largest black holes in the universe are far more powerful than anything formed by dying stars. These cosmic giants sit at the centers of galaxies. They control the motion of billions of stars, and they can unleash energy powerful enough to shape the evolution of entire galaxies. These are the supermassive black holes, and their story is even more astonishing than the journey into a black hole itself. Supermassive black holes are among the most extraordinary objects ever discovered. While many black holes form when massive stars collapse, supermassive black holes exist on a completely different scale. These cosmic giants can contain millions, billions, or even tens of billions of times the mass of our Sun, and almost every large galaxy in the universe appears to have one sitting at its center, including our own. At the heart of the Milky Way lies a supermassive black hole known as Sagittarius A star. This object contains about 4 million times the mass of the Sun. Despite its enormous mass, it occupies a region of space smaller than our solar system. Stars near the center of the galaxy orbit it at incredible speeds. Some complete their orbit in just a few years. Astronomers have been tracking these stars for decades. By measuring their motion, scientists were able to calculate the mass of the invisible object pulling on them. The only explanation that fit the observations was a supermassive black hole. For a long time, Sagittarius A star remained invisible, but in 2022, scientists achieved a historic breakthrough. Using a global network of radio telescopes known as the Event Horizon Telescope, astronomers captured the first image of the black hole at the center of our galaxy. The image revealed a glowing ring of gas surrounding a dark central shadow. That shadow marked the event horizon, the boundary beyond which nothing can escape. This image confirmed decades of theoretical predictions about black holes. But Sagittarius A star is actually relatively small compared to some other supermassive black holes. In the galaxy Messier 87, astronomers discovered a black hole containing about 6.5 billion times the mass of the Sun. It was the first ever to be photographed in 2019. Its event horizon is larger than the orbit of Pluto, and it powers a gigantic jet of particles that stretches thousands of light years into space. These jets are among the most powerful structures in the universe. They form when matter spirals toward the black hole through an accretion disk. Inside the disk, friction heats the gas to extraordinary temperatures. Magnetic fields twist and accelerate particles along the black hole's rotational axis. The particles shoot outward at nearly the speed of light, forming enormous beams that can extend far beyond the galaxy itself. Some of these jets stretch for millions of light years. They carry enormous amounts of energy into intergalactic space. These jets can heat the gas surrounding a galaxy and even prevent new stars from forming. In this way, supermassive black holes may regulate the growth of galaxies. Without them, galaxies might grow far larger and form stars much more rapidly. But sometimes these black holes become even more active. When a large amount of matter falls toward a supermassive black hole, the energy released can transform the entire galaxy. The accretion disk becomes extremely bright. Radiation pours out across the electromagnetic spectrum. The center of the galaxy can outshine all of its stars combined. These incredibly bright objects are known as quasars. Quasars are among the most luminous objects in the entire universe. Some are so bright that they can be seen from billions of light years away. When we observe distant quasars, we are actually seeing the universe as it existed when it was very young, only a few 100 million years after the Big Bang. The discovery of these ancient quasars created a major puzzle for astronomers. Contain black holes with masses of strong billions of suns. But the universe was still very young at that time. How could black holes grow so large so quickly? Scientists are still trying to answer that question. One possibility is that enormous clouds of gas in the early universe collapsed directly into black holes without forming stars first. These objects are known as direct collapse black holes. Instead of starting small and slowly growing larger, these black holes may have begun their lives already containing hundreds of thousands of solar masses. Another possibility is that the first generation of stars, known as strong population 3 stars, were extremely massive. When these stars collapsed, they may have produced unusually large black holes. Over time, repeated mergers between black holes could have created the supermassive giants we observe today. Telescopes are helping astronomers investigate these possibilities. In recent years, the James Webb Space Telescope has begun observing galaxies from the earliest periods of cosmic history. Some of these galaxies appear to contain surprisingly massive black holes. This suggests that black holes may have grown much faster in the early universe than scientists previously believed. As we continue exploring the cosmos, we may soon discover how these cosmic giants formed. But black holes do not always remain quietly at the centers of galaxies. Sometimes they collide. When two galaxies merge, their central black holes eventually begin orbiting each other. Over millions of years, they spiral closer together. Their orbit shrinks as they emit gravitational waves. Eventually, the two black holes collide and merge into a single larger black hole. This collision releases an enormous burst of gravitational waves that ripple across the universe. These waves stretch and compress space itself as they travel out. Modern gravitational wave detectors such as LIGO have already observed several black hole mergers. Future detectors will be able to observe collisions between supermassive black holes. These events will reveal how galaxies grow and merge over billions of years. But even the largest black holes are not eternal. According to quantum physics, black holes slowly lose energy through Hawking radiation. This radiation causes them to shrink very slowly over time. For supermassive black holes, the process takes incredibly long. Far longer than the current age of the universe. But eventually, even these cosmic giants will fade away. In the distant future, after all stars have burned out and galaxies have grown dark, black holes may be the last remaining objects in the universe. This future period is sometimes called the black hole era. During this era, the cosmos will be filled with black holes, slowly evaporating through Hawking radiation. One by one, they will shrink and disappear. The final black holes may survive for 10 to the power of 100 years or more. But eventually, even they will vanish. When the last black hole evaporates, the universe will become an incredibly quiet place. Only thin radiation and scattered particles will remain. A cold, dark universe, stretching endlessly through space. Yet even that distant future is not the end of the story, because the study of black holes continues to reveal new mysteries. Each discovery raises new questions about the nature of space and time, and every observation pushes our understanding of physics further. Black holes may help us discover the true theory of quantum gravity. They may reveal the origin of the universe, help us understand whether multiple universes exist. These possibilities remain uncertain, but one thing is clear. Black holes are not just the most extreme objects in the cosmos. They are also some of the most important, because hidden within their darkness may lie the answers to some of the deepest questions humanity has ever asked. What is space? What is time? And what are the fundamental laws that govern the universe itself? The search for those answers continues, and black holes remain one of the most powerful clues we have, because sometimes the greatest secrets of the universe are hidden in the darkest places. Black holes do not simply sit quietly in space. They interact constantly with their surroundings, shaping the galaxies around them in ways scientists are still trying to understand. One of the most dramatic interactions occurs when a star wanders too close to a black hole. Stars normally orbit safely around the centers of galaxies, but occasionally their paths bring them dangerously near the immense gravitational pull of a supermassive black hole. When this happens, the star experiences an intense gravitational gradient. The side of the star closest to the black hole feels a stronger pull than the far side. At first, the star begins to stretch slightly, but as it moves closer, the tidal forces become overwhelming. Eventually, the star is torn apart completely. This violent process is called a tidal disruption event. The star is ripped into long streams of glowing gas that spiral around the black hole. Some of this gas escapes into space, but much of it forms a swirling accretion disk around the black hole. Inside this disk, particles collide at incredible speeds. Friction heats the gas to millions of degrees. The glowing disk emits enormous bursts of radiation that can be detected across the universe. For a brief period, the dying star produces a brilliant flare, brighter than an entire galaxy. Astronomers have observed several of these events using space telescopes. Each one provides valuable clues about how black holes feed and grow. But black holes are not only powerful destroyers, they are also engines of energy. When matter falls into a black hole, it releases more energy than almost any other process in the universe. This is because gravity converts the potential energy of falling matter into heat and radiation. In some cases, nearly 40% of the mass of the infalling material can be converted into energy. This efficiency is far greater than the energy produced by nuclear fusion in stars. As a result, black holes can power some of the brightest objects in existence. Quasars, for example. As our understanding of black holes grows, scientists have begun to realize that these mysterious objects may influence the universe in ways far beyond what we once imagined. For many years, black holes were thought to be simple endpoints of stellar evolution, the final stage in the life of a massive star. Once formed, they were believed to sit quietly in space, swallowing whatever matter drifted too close. But modern observations have revealed a much more complex picture. Black holes are dynamic objects that interact constantly with their surroundings. They shape galaxies. They generate powerful radiation. They send gravitational waves rippling across the cosmos. And in some cases, they may even influence the formation of new stars. To understand how this happens, we need to examine the environment surrounding a black hole. When gas, dust, or stars move near a black hole, they rarely fall directly into it. Instead, the material begins orbiting the black hole. Over time, collisions between particles cause the material to settle into a flattened disk around the black hole. This structure is called an accretion disk. Inside the disk, particles move at incredible speeds. Particles generates enormous amounts of heat. Temperatures can rise to millions of degrees. At these temperatures, the gas emits powerful radiation in the form of X-rays and gamma rays. This radiation can travel across vast distances in space, allowing astronomers to detect black holes that would otherwise remain invisible. In fact, many black holes are discovered not by observing the black hole itself, but by detecting the intense radiation produced by their accretion disks. But accretion disks are not the only structures that form around black holes. Some black holes also produce powerful outflows of matter. These outflows occur when magnetic fields surrounding the black hole accelerate charged particles out. The particles shoot away from the black hole along its rotational axis, forming enormous jets. These relativistic jets can travel at speeds close to the speed of light. Some extend for thousands or even millions of light years. The energy carried by these jets can have dramatic effects on the surrounding galaxy. They can heat interstellar gas. They can push gas away from the center of the galaxy. They can even trigger the formation of new stars by compressing gas clouds. This process is known as black hole feedback. It describes the way energy released by a black hole influences the evolution of its host galaxy. Without this feedback mechanism, galaxies might grow uncontrollably. Stars would form much more rapidly. Galaxies could become far larger and more chaotic than those we observe today. In this sense, black holes may act as regulators that help maintain balance in galaxies, but the role of black holes may extend even further. Some scientists believe that black holes could provide clues about the very beginning of the universe. Shortly after the Big Bang, the universe was filled with hot, dense matter. Tiny fluctuations in density may have caused certain regions of space to collapse under their own gravity. If these regions were dense enough, they might have formed primeval black holes. Unlike black holes formed by dying stars, primeval black holes could have formed directly from the conditions of the early universe. Some might have been very small, perhaps no larger than a mountain. Others might have grown much larger. If primordial black holes exist, they could help explain one of the greatest mysteries in cosmology, the nature of dark matter. Dark matter is an invisible substance that makes up most of the matter in the universe. It does not emit or absorb light, which makes it extremely difficult to detect. But its gravitational influence can be observed in the motion of galaxies and galaxy clusters. Some researchers have suggested that a population of primordial black holes could account for at least part of dark matter. Although this idea remains controversial, ongoing observations continue to test the possibility. If primordial black holes are ever confirmed, they would reveal new information about the earliest moments of cosmic history. They would show how gravity shaped the universe during its infancy. But even without primordial black holes, the universe already contains an astonishing number of black holes. Astronomers estimate that the Milky Way galaxy alone may contain over 100 million black holes. Most of these objects are invisible. They wander quietly through the galaxy, detectable only by their gravitational effects. Some may even drift through the empty space between stars. These wandering objects are sometimes called rogue black holes. Although they sound frightening, the chances of one passing close to Earth are extremely small. Space is unimaginably vast. Even in our galaxy, the average distance between stars is several light years. Black holes are scattered throughout this enormous volume of space. But their existence reminds us that the universe contains many hidden objects that we cannot see directly. Behind the familiar stars in the night sky lies a hidden universe filled with neutron stars, dark matter, and black holes. Each new discovery reveals another layer of complexity in the cosmos, and each layer raises new questions. Black holes, once considered theoretical curiosities, have become central to our understanding of astrophysics. They influence the growth of galaxies. They produce gravitational waves. They challenge our understanding of space and time. And they may hold the key to solving some of the deepest puzzles in physics. Because inside a black hole lies one of the most extreme environments in the universe. Gravity becomes incredibly strong. Space and time are warped beyond recognition, and the laws of physics may behave in ways we have not yet discovered. Understanding these extreme conditions could help scientists develop a theory that unifies gravity with quantum mechanics. Such a theory would revolutionize our understanding of the universe. It could explain the behavior of matter at the smallest scales. It could reveal the true structure of space-time. And it could answer questions about the origin and fate of the cosmos. But developing such a theory will not be easy. It may require new experiments, new observations, and entirely new ways of thinking about the nature of reality. Black holes sit at the boundary between the known and the unknown. They challenge our assumptions. They force us to confront the limits of our understanding. Holds many secrets waiting to be discovered. Because no matter how much we learn about black holes, they always seem to reveal new mysteries. Each discovery opens the door to deeper questions, and each question pushes us further toward understanding the true nature of the cosmos. The study of black holes is far from complete. In many ways, it has only just begun. As new telescopes and detectors come online in the coming decades, scientists will explore black holes with unprecedented precision. They will observe the motion of matter near event horizons. They will detect gravitational waves from distant collisions. They will peer deeper into the centers of galaxies. And with each new observation, humanity will move closer to answering one of the most profound questions in science. What are the ultimate laws that govern the universe? Black holes may hold the key. Hidden within their darkness may lie the answers to mysteries that have puzzled humanity for centuries. And as we continue exploring the universe, these mysterious objects will remain among the most fascinating and important discoveries of modern science. Because sometimes the darkest places in the cosmos reveal the brightest truths about how the universe truly works. Black holes also force us to rethink something very fundamental about the universe: the nature of information. In everyday life, information seems simple. A book contains words, a computer contains data. A photograph stores an image of a moment in time. But in physics, information has a much deeper meaning. Information describes the exact state of every particle in a system, its position, its momentum, its energy, and its quantum properties. According to the laws of quantum mechanics, this information can never truly be destroyed. It can be scrambled, it can be hidden, but it cannot disappear completely. Yet black holes appear to do exactly that. When an object falls into a black hole, all of the detailed information about that object seems to vanish. Imagine throwing a library of books into a black hole. The mass of the black hole would increase slightly, but all the words, all the ideas, all the information inside those books would appear to be lost forever. This contradiction between black holes and quantum mechanics created one of the greatest puzzles in modern physics. Black hole information paradox. For decades, scientists debated possible solutions. Some physicists argued that information truly is destroyed by black holes, but this idea conflicts with the basic principles of quantum theory. Others suggested that information might somehow escape from black holes through Hawking radiation. However, Hawking radiation appears almost completely random, making it difficult to see how it could contain meaningful information. In recent years, new theoretical ideas have begun to shed light on this puzzle. One promising concept is the holographic principle. This idea suggests that the information contained within a region of space may actually be encoded on its boundary. In the case of a black hole, that boundary would be the event horizon. According to this view, everything that falls into a black hole leaves a subtle imprint on the event horizon. Surface of the black hole acts like a kind of cosmic memory. Although the information becomes extremely scrambled, it is never truly lost. Over incredibly long periods of time, this information might gradually leak back into the universe through Hawking radiation. While the details are still being studied, this idea has gained support among many physicists. It suggests that black holes do not violate the laws of quantum mechanics after all. Instead, they may preserve information in ways that are far more complex than we originally imagined. But black holes may hold even deeper insights. Some researchers believe that understanding black holes could reveal the true structure of space and time. At the smallest scales imaginable, far smaller than atoms, space itself may not be smooth and continuous. Instead, it may be composed of tiny quantum units. Some theories suggest that space-time might behave like a network of interconnected pieces. Others propose that the universe could have additional dimensions beyond the 3 dimensions of space and 1 dimension of time that we experience. Black holes may provide a unique window into these hidden aspects of reality. Because near the event horizon, gravity becomes so intense that the structure of space-time itself begins to stretch and distort dramatically. Studying these extreme environments may reveal clues about the deeper nature of the universe. In fact, some of the most exciting developments in theoretical physics have come from studying black holes. One surprising discovery is that the mathematics used to describe black holes often appears in other areas of physics. For example, similar equations appear in studies of quantum information, thermodynamics, and even condensed matter systems. This suggests that black holes may be connected to fundamental principles that apply across many different areas of science. One particularly fascinating connection involves the concept of entropy. Entropy is a measure of disorder or randomness in a system. In the 1970s, physicists discovered that black holes appear to possess entropy. In fact, the entropy of a black hole is proportional to the area of its event horizon. This relationship is known as the Bekenstein-Hawking entropy formula. It was a surprising discovery because it suggested that black holes obey the laws of thermodynamics, just like ordinary physical systems. This insight opened a new field of research known as black hole thermodynamics. Scientists realized that black holes behave in ways similar to heat engines. They have temperature, they emit radiation, and they evolve over time. These discoveries hint at a deep connection between gravity, quantum physics, and thermodynamics. Connection may lead to a new theory that explains how the universe works at the most fundamental level. Black holes may therefore be more than just astronomical objects. They may be keys to unlocking the deepest laws of nature. But while theoretical physicists explore these ideas with equations and computer models, astronomers continue observing black holes across the universe. New telescopes are allowing scientists to study these objects in greater detail than ever before. The Event Horizon Telescope is being expanded to include more observatories around the world. Future upgrades will allow astronomers to capture even sharper images of black holes. These images may reveal the structure of accretion disks and magnetic fields near event horizons. Space-based gravitational wave detectors are also being developed. One of the most ambitious projects is the Laser Interferometer Space Antenna, LISA. This mission will place 3 spacecraft in orbit around the Sun. They will form a giant triangular detector millions of kilometers across. LISA will be able to detect gravitational waves from supermassive black hole mergers across the universe. These signals will provide new insights into how galaxies grow and evolve. Meanwhile, powerful telescopes such as the strong James Webb Space Telescope continue searching for the earliest black holes that formed after the Big Bang. Each discovery adds another piece to the puzzle. And with each new observation, our understanding of black holes becomes deeper. Yet the biggest mysteries remain unsolved. What exactly happens at the singularity? How does gravity behave at the quantum level? Is space-time truly continuous, or is it made of tiny discrete units? And could black holes connect to other regions of the universe? Questions remain open, but history shows that the universe often reveals its secrets when we least expect. Just a century ago, black holes were considered mathematical curiosities. Today they are central to modern astrophysics, and tomorrow they may lead to discoveries that transform our understanding of reality itself. Because when we study black holes, we are not just studying distant objects in space. We are exploring the deepest foundations of the universe. We are asking questions about the nature of time, about the structure of space, about the ultimate fate of matter and energy. And every answer we find brings us one step closer to understanding the cosmos. Black holes remind us that the universe is not simple. It is vast, it is mysterious, and it is filled with wonders that challenge our imagination. But that is exactly what makes the search worthwhile. Darkness of these cosmic giants lies knowledge that could reshape our understanding of everything, and humanity has only just begun to uncover those secrets. As we continue to study black holes, one realization becomes increasingly clear. These objects are not merely distant curiosities scattered across the cosmos. They are central players in the story of the universe. Every galaxy we observe seems to carry the signature of a black hole at its core. These hidden giants influence the motion of stars, the flow of gas, and the birth of new stellar systems. In many ways, galaxies and their central black holes appear to grow together, almost as if they are linked in a cosmic partnership. Astronomers have discovered that the mass of a galaxy's central black hole is closely related to the mass of the galaxy's central bulge of stars. This relationship is too consistent to be a coincidence. It suggests that the growth of galaxies and the growth of black holes are connected through powerful feedback processes. When a black hole consumes matter, the energy released can travel outward across enormous distances. Jets and radiation from the accretion disk can push gas away from the galactic center, slowing down the formation of new stars. In other cases, these outflows compress gas clouds and trigger bursts of star formation. In this way, black holes act almost like cosmic thermostats, regulating the growth of their host galaxies. But the influence of black holes is not limited to individual galaxies. On even larger scales, they may help shape clusters of galaxies and the vast web-like structure of the universe itself. The universe is filled with enormous clusters containing hundreds or thousands of galaxies bound together by gravity. At the centers of these clusters, supermassive black holes often release tremendous amounts of energy into the surrounding gas. This energy prevents the gas from cooling too quickly and collapsing into new stars. Without this effect, galaxy clusters might look very different from the ones we observe today. Once again, we see that black holes are not simply destructive forces. They are part of the delicate balance that shapes cosmic evolution. Yet despite their enormous influence, black holes remain incredibly difficult to observe directly. Because no light escapes from within the event horizon, astronomers must rely on indirect evidence to study them. One of the most powerful techniques involves tracking the motion of nearby stars. In the center of the Milky Way, astronomers have spent decades observing stars orbiting Sagittarius A star. These stars move at incredible speeds, completing their orbits in just a few years. By analyzing these motions, scientists can calculate the mass of the invisible object at the center of the galaxy. The results confirm that a supermassive black hole must be present. Similar observations have been made in many other galaxies. In each case, the same conclusion appears. Black holes are almost universal features of large galaxies. But observing stars is only one method. Astronomers also study the radiation emitted by matter falling into black holes. Accretion disks glow intensely as gas heats up to millions of degrees. Space telescopes sensitive to X-rays can detect this radiation even when the black hole itself remains hidden. Another method involves detecting gravitational waves produced by black hole mergers. When two black holes spiral together and collide, they create ripples in space-time that travel across the universe. These ripples carry information about the masses and motions of the merging object. Gravitational wave observatories allow scientists to study black holes that would otherwise be invisible. Each of these techniques provides a different piece of the puzzle. Together, they allow astronomers to build an increasingly detailed picture of black holes and their role in the cosmos. Yet many mysteries remain. One of the most puzzling questions involves the earliest black holes in the universe. Observations suggest that supermassive black holes existed when the universe was less than 1 billion years old. These objects must have formed extremely quickly after the Big Bang. How could such enormous objects appear so early? Scientists are still searching for answers. Some theories propose that giant gas clouds collapsed directly into black holes before stars had time to form. Others suggest that clusters of massive stars merged together and collapsed into black holes that grew rapidly by consuming surrounding matter. The James Webb Space Telescope is helping astronomers explore this early period of cosmic history. By observing distant galaxies whose light has traveled billions of years to reach us, Webb allows scientists to study the universe when it was still very young. Already, these observations are revealing surprising results. Some early galaxies appear to contain black holes larger than expected, suggesting that black hole formation may have occurred faster than current models predict. As more data is collected, we may soon gain a clearer understanding of how the first black holes formed. But black holes are not only important for understanding the past of the universe, they may also play a role in its distant future. Over incredibly long timescales, stars will exhaust their nuclear fuel and fade away. Galaxies will grow dim as the formation of new stars slows to a halt. Eventually, the universe may enter an era dominated by black holes. During this time, most of the remaining mass in the cosmos will exist in the form of black holes slowly drifting through space. But even these objects will not last forever. As Stephen Hawking showed, black holes slowly lose mass through Hawking radiation. Over unimaginable periods of time, they will gradually evaporate. Small black holes disappear more quickly than large ones. But even the most massive black holes will eventually fade away. The final black holes in the universe may survive for more than 10 to the power of 100 years, a number so large it is almost impossible to comprehend. Yet even that immense span of time will eventually pass. When the last black hole evaporates, the universe will be left in a state sometimes called the heat death of the cosmos. Matter will be scattered thinly across an enormous volume of space. Energy will be evenly distributed, leaving no sources of structure or activity. It will be a quiet and nearly empty universe. But that future lies unimaginably far away. For now, the universe remains vibrant and full of activity. Stars are forming in distant galaxies. Black holes are merging and sending gravitational waves across space. New discoveries are being made every year as telescopes and detectors become more powerful. And each discovery brings us closer to answering some of the deepest questions in science. What is the true nature of space-time? How do gravity and quantum mechanics fit together? What lies beyond the event horizon? These questions continue to inspire scientists around the world, because black holes represent more than just extreme astrophysical objects. They represent the limits of our knowledge, and exploring those limits is one of the most important goals of modern science. Science. Every time we learn something new about black holes, we take another step toward understanding the universe itself. The journey is far from over. In fact, it may only be beginning, because somewhere in the depths of space, hidden within the shadows of black holes, the next great discovery may already be waiting. And when it arrives, it could change the way we see the universe forever. As scientists continue to investigate black holes, one of the most exciting frontiers is the possibility of observing their behavior in real time. For most of human history, the universe appeared static. Stars seemed fixed in the sky, galaxies looked like distant smudges of light, and cosmic change unfolded far too slowly to witness directly. But modern instruments are beginning to change that. Today, astronomers can observe black holes devouring stars, launching jets of plasma, and merging with one another in spectacular cosmic events. These observations are allowing scientists to watch some of the most extreme processes in the universe as they happen. One example comes from tidal disruption events, those violent moments when a star wanders too close to a black hole. When such an encounter occurs, telescopes around the world quickly turn toward the source. Within days or even hours, astronomers can watch the light from the shredded star flare into existence. The brightness rises dramatically as gas spirals into the black hole's accretion disk. Then, over weeks or months, the flare slowly fades as the remaining material is consumed. By studying these events in detail, scientists learn how black holes feed and how matter behaves under intense gravitational forces. But tidal disruption events are only part of the story. Another extraordinary phenomenon occurs when matter in an accretion disk becomes unstable. Sometimes, the disk suddenly releases a burst of energy that sends shock waves through the surrounding gas. These eruptions can produce powerful flashes of X-rays or gamma rays that travel across the universe. Space telescopes such as NASA's Chandra X-ray Observatory and NuSTAR monitor these energetic events. Their observations help astronomers understand how black holes interact with their environment. Meanwhile, gravitational wave detectors continue to reveal new black hole collisions. Every time two black holes merge, the event produces a characteristic pattern of gravitational waves. The signal rises in frequency as the black holes spiral closer together, creating what scientists call a chirp. This chirp contains information about the masses and spins of the merging black holes. By analyzing the signal, scientists can reconstruct the final moments before the collision. These observations have already revealed surprises. Some black holes involved in mergers are far more massive than expected. Others appear to have formed through unusual processes, perhaps inside dense star clusters where repeated collisions occur. As gravitational wave observatories become more sensitive, scientists expect to detect hundreds or even thousands of black hole mergers each year. Future detectors may even observe the collision of supermassive black holes at the centers of merging galaxies. Such events would release gravitational waves powerful enough to ripple across the entire observable universe. The study of black holes is therefore entering a new era, one where astronomers can observe their behavior across multiple forms of radiation and gravitational signals. This approach is known as multi-messenger astronomy. By combining information from light, gravitational waves, and even neutrinos, scientists gain a much more complete picture of cosmic events. Black holes, once invisible and mysterious, are becoming some of the best studied objects in astrophysics. Yet even with these advances, the most important questions remain unanswered. One of the deepest mysteries involves the true nature of the event horizon. According to general relativity, the event horizon is simply a boundary in space-time. But some physicists believe that quantum effects could dramatically alter its structure. One controversial idea suggests that the event horizon might contain something called a firewall, an intense region of energy that would instantly destroy anything crossing it. If firewalls exist, they would violate one of the key predictions of general relativity. Other scientists argue that no such firewall exists, and that the event horizon behaves exactly as Einstein predicted. Resolving this debate may require new observations or entirely new theories of physics. Another mystery involves the possibility that black holes may store information on their surfaces in extremely subtle ways. The holographic principle suggests that the three-dimensional universe we experience might actually be encoded on a two-dimensional boundary. Black holes provide one of the clearest examples of this idea. If the holographic principle is correct, it could revolutionize our understanding of space-time and quantum gravity. Some physicists even speculate that the entire universe might behave like a giant hologram. These ideas remain highly theoretical, but they show how black holes continue to push the boundaries of scientific thought. Every time researchers attempt to understand these objects, they uncover new connections between different areas of physics. Black holes link gravity, quantum mechanics, thermodynamics, and information theory in ways that are still not fully understood. Because of this, they are often described as the ultimate testing ground for fundamental physics, and that is why scientists continue to study them so intensely. Each new observation, each new theoretical insight, brings us closer to answering questions that have puzzled humanity for centuries. Questions about the origin of the universe, questions about the nature of time, questions about the ultimate fate of matter and energy. Black holes lie at the heart of many of these mysteries. They represent the places where our current knowledge reaches its limits, but they also represent opportunities to discover new physics, opportunities to expand our understanding of the cosmos, and perhaps even opportunities to glimpse the deeper structure of reality itself. When we look into the darkness of a black hole, we are not simply observing an object in space. We are confronting one of the most profound mysteries in the universe, a mystery that challenges our understanding of how the cosmos works. These mysteries that drive scientific discovery. Because every great breakthrough in science begins with a question that seems impossible to answer. Black holes are full of such questions. What lies beyond the event horizon? What happens to matter at the singularity? How does gravity behave at the quantum level? And could black holes hold the key to a deeper theory that explains everything? The answers may not come quickly. They may take decades or even centuries to uncover. But the search itself is one of humanity's greatest intellectual adventures. With each new telescope, each new detector, and each new idea, we move closer to understanding these extraordinary objects. And as we continue exploring the universe, black holes will remain among the most fascinating and mysterious phenomena we encounter, because sometimes the darkest regions of the cosmos reveal the brightest insights into how the universe truly works. Part 3. The Death of Black Holes. For a long time, scientists believed that black holes were eternal. Once something fell inside, it was gone forever. The black hole would simply sit in space, growing larger as it consumed more matter. Nothing could escape it. Nothing could destroy it. Black holes were thought to be the ultimate end of matter in the universe. But in the 1970s, a young physicist named Stephen Hawking made a discovery that changed everything. According to Hawking's calculations, black holes are not completely black. They slowly leak energy, and over incredibly long periods of time, they can die. This discovery was shocking because it combined two areas of physics that had never been successfully unified: quantum mechanics and gravity. To understand Hawking's idea, we first need to examine something very strange about empty space. According to classical physics, empty space is truly empty. Nothing exists there. But quantum mechanics tells a very different story. In quantum theory, space is actually filled with tiny fluctuations of energy. These fluctuations constantly create pairs of particles and antiparticles. The particles appear for a brief moment, then they annihilate each other and disappear again. These are known as virtual particles. They pop in and out of existence everywhere in the universe, even in what appears to be completely empty space. Normally, these particle pairs vanish almost instantly, but near a black hole, something unusual can happen. Imagine a pair of virtual particles forming just outside the event horizon. One particle falls into the black hole. The other escapes into space. Because the pair never recombines, the escaping particle becomes real. To an outside observer, it appears as if the black hole has emitted a particle. In other words, the black hole is slowly losing energy. This phenomenon is known as Hawking radiation, and it means that black holes are not completely eternal after all. They slowly evaporate. But the process is extremely slow. For a black hole with the mass of our Sun, the evaporation time would be roughly 10 to the 67 years. To put that in perspective, the universe today is only about 13.8 billion years old. That means a stellar black hole would survive for far longer than all stars, galaxies, and planets combined. But the smaller a black hole becomes, the faster it evaporates. As the black hole shrinks, its temperature increases. This causes it to emit radiation more rapidly. Eventually, the black hole enters its final stage of evaporation. In the last moments of its life, the black hole releases a sudden burst of energy. Then it disappears completely. But this discovery raised another enormous question. What happens to everything that fell inside them? This problem became known as the black hole information paradox. According to quantum mechanics, information can never be destroyed. Every particle contains information about its state. Even if particles interact, collide, or transform, that information must still exist somewhere. But if a black hole completely evaporates, it seems as if the information about everything that fell inside it would be lost forever. For decades, physicists struggled with this paradox. Some believed information might truly disappear. Others argued that quantum mechanics must somehow preserve it. One possible solution came from the idea of the holographic universe. According to this concept, the information contained inside a black hole may actually be stored on its event horizon. The surface of the black hole could behave like a giant two-dimensional memory device. Everything that falls inside leaves a subtle imprint on that surface. Over time, the information might slowly escape through Hawking radiation. Although the details are still being studied, many physicists now believe that information is not destroyed by black holes after all. Instead, it becomes extremely scrambled. Recovering it may be practically impossible, but in principle, it still exists. This insight has profound implications for our understanding of the universe. It suggests that the fundamental laws of physics remain consistent, even in the most extreme environment. But Hawking radiation also tells us something else. Black holes will not last forever. In the distant future, the universe will enter a strange new era, an era dominated by black holes. This period is known as the black hole era. To understand this era, we must imagine the universe billions upon billions of years from now. Stars will eventually exhaust their nuclear fuel. They will fade into white dwarfs, neutron stars, and black holes. Galaxies will slowly grow darker as star formation comes to an end. After about 100 trillion years, most stars in the universe will have burned out. The cosmos will become a much quieter place, but black holes will remain. Over time, gravitational interactions will cause many objects in galaxies to fall into central black holes. Others will be ejected into intergalactic space. Eventually, most of the remaining matter in the universe will end up inside black holes. The universe will be dominated by these dark objects. But even during the black hole era, Hawking radiation will continue its slow work. Black holes will gradually lose mass. Smaller black holes will disappear first. Larger ones will survive for much longer. Black holes, containing billions of solar masses, may last for up to 10 to the power of 100 years. That number is so large it is difficult to imagine. It is a 1 followed by 100 zeros. Yet even that enormous time span will eventually pass. One by one, the last black holes will evaporate. Each will release a final burst of radiation before disappearing. When the final black hole vanishes, the universe will enter its final stage, a period sometimes called the Dark Era. During this era, the cosmos will contain almost nothing. Only scattered particles and low-energy radiation will remain. There will be no stars, no galaxies, no black holes, just a vast cold universe expanding forever. Yet even this bleak future may not be the end of the story. Some cosmologists have proposed that new universes might form through quantum fluctuations. Others speculate that black holes themselves may create new universes inside their event horizon. If this idea is correct, every black hole could contain an entire cosmos beyond our reach, and our own universe might even have begun as the interior of a black hole in another universe. These ideas remain speculative, but they highlight the profound mysteries that black holes continue to raise. They remind us that the universe is far more complex and surprising than we once believed. Black holes were once thought to be the ultimate destroyers of matter and information. Today, we know they are far more than that. They are laboratories for extreme physics. They connect quantum mechanics, gravity, and thermodynamics. They shape the evolution of galaxies, and they may hold clues about the deepest laws governing reality itself. In many ways, black holes represent the boundary between what we understand and what we do not, waiting to be solved. And as our technology improves and our theories evolve, scientists will continue exploring these mysterious objects, because somewhere within the darkness of black holes, the next great discovery about the universe may be waiting. Even though the distant future of the universe may seem unimaginably bleak, the study of black holes continues to reveal new layers of mystery and possibility. These objects, once thought to be simple gravitational traps, now appear to sit at the crossroads of several of the deepest ideas in physics. One of the most intriguing insights to emerge from black hole research is the connection between gravity and thermodynamics. In everyday life, thermodynamics governs how heat and energy move. It explains why hot coffee cools down, why engines produce waste heat, and why systems naturally move toward greater disorder over time. This tendency toward disorder is described by a quantity known as entropy. Entropy measures how many microscopic ways a system can arrange itself while still appearing the same on a large scale. For example, a deck of cards shuffled into random order has higher entropy than a deck arranged neatly by suit and number. For a long time, physicists believed that black holes had no entropy at all. After all, they appeared to erase all information about the objects that fell inside them. But in the early 1970s, a physicist named Jacob Bekenstein proposed something revolutionary. He suggested that black holes must possess entropy. His reasoning was simple, but profound. If a black hole had no entropy, then throwing an object with entropy into it would cause entropy in the universe to decrease. But that would violate the second law of thermodynamics, which states that total entropy in the universe must never decrease. To resolve this problem, Bekenstein proposed that the entropy of a black hole is proportional to the area of its event horizon. Later, Stephen Hawking's work on black hole radiation confirmed this idea. Together, their results produced the famous Bekenstein-Hawking entropy formula. According to this formula, the entropy of a black hole depends not on its volume, but on the surface area of its event horizon. This was a startling discovery. In most physical systems, entropy depends on volume, the amount of space a system occupies. But for black holes, the entropy depends only on the surface. This strange result hinted at a deeper principle in physics. Perhaps the fundamental information describing a region of space is encoded on its boundary rather than inside it. This idea eventually evolved into the holographic principle. According to the holographic principle, the entire universe might be describable as information encoded on a lower dimensional boundary. Just as a hologram can create the illusion of three-dimensional depth using a two-dimensional surface, the three-dimensional world we experience might arise from information stored on a distant cosmic boundary. Although this concept sounds almost surreal, it has gained serious attention among theoretical physicists. In certain models of quantum gravity, the holographic principle appears naturally in the mathematics. Black holes therefore play a crucial role in exploring these ideas. They are one of the few places where gravity, thermodynamics, and quantum mechanics all interact in a measurable way. Studying black holes may therefore reveal the hidden structure of reality itself. But black holes also raise questions about the limits of knowledge, because once something crosses the event horizon, it becomes permanently hidden from the outside universe. No signal can escape. No observation can reveal what happens inside. This means that some aspects of black holes may always remain beyond our reach. They represent a boundary not only in space-time, but in our ability to observe and measure the universe. And yet, despite this barrier, scientists have found creative ways to study black holes indirectly. Simulations allow researchers to model how matter behaves near event horizons. These simulations reproduce many of the patterns observed by telescopes. They help scientists predict how accretion disks evolve and how jets are launched. Laboratory experiments have even created analog black holes using fluids and sound waves. In these experiments, researchers simulate event horizons by creating regions where sound waves cannot escape. These systems allow scientists to study phenomena similar to Hawking radiation under controlled conditions. Although these analog systems are not true black holes, they provide valuable insights into the physics of horizons and quantum fields. Meanwhile, astronomical observations continue to advance. New telescopes are being built that will observe the universe with unprecedented sensitivity. Future instruments may be able to track the motion of matter extremely close to event horizons. They may capture movies of black hole shadows changing over time. They may detect gravitational waves from the earliest black hole mergers in the young universe. Each of these observations will bring us closer to understanding these mysterious objects. But even as technology improves, black holes remain profoundly mysterious. They challenge our deepest assumptions about the nature of reality. They force us to reconsider what we mean by space, time, and information. And they remind us that the universe still contains regions where our current theories fail. That is why black holes continue to inspire scientists and the public alike. They represent the ultimate frontier of astrophysics, a place where imagination, mathematics, and observation meet. And perhaps the most remarkable thing about black holes is how our understanding of them has evolved. Just over a century ago, they existed only as strange, mathematical solutions to Einstein's equation. Many scientists believed they could never exist in reality. Today we know that black holes populate the universe in vast numbers. We have detected their gravitational waves. We have observed their shadows. We have measured their influence on stars and galaxies. And yet the deeper we explore them, the more mysteries they reveal. Because black holes are not simply endpoints of cosmic evolution. They are gateways to deeper questions about the universe. Questions about the origin of space-time. Questions about the nature of quantum reality. Questions about the ultimate fate of matter and energy. In many ways, black holes represent the limits of our knowledge. But they also represent the beginning of new discoveries. Because every time humanity has approached the edge of understanding, we have eventually found new ways to push beyond it. May once again lead us to a revolution in physics, one that changes our understanding of the cosmos forever. Somewhere in the darkness of these cosmic giants lies a deeper truth about how the universe works. And as long as we continue exploring, questioning, and observing, that truth will slowly come into view. The story of black holes is therefore not just a story about gravity or astronomy. It is a story about curiosity, a story about the human desire to understand the universe. And that story is far from finished. As we look deeper into the universe, black holes increasingly appear not as isolated curiosities but as essential components of cosmic evolution. They influence the formation of galaxies, shape the behavior of matter under extreme conditions, and push our physical theories to their limits. Yet one of the most fascinating aspects of black holes is how their study has reshaped our understanding of space and time. Before Einstein, space and time were thought to be separate, unchanging backgrounds against which the events of the universe unfold. But general relativity revealed that space and time are woven together into a single fabric known as space-time. Mass and energy bend this fabric, and objects move along the curves created by that bending. Black holes represent the most extreme example of this phenomenon. Near a black hole, space-time becomes so distorted that paths through space inevitably lead inward. Even light cannot escape once it passes the event horizon. This distortion produces some remarkable effects. Light from distant stars can be bent into arcs or rings around the black hole. Time itself slows dramatically as gravity grows stronger. To a distant observer, a clock near a black hole appears to tick more slowly. These predictions have been confirmed through observations near massive objects and through experiments with extremely precise atomic clocks. But near a black hole, the effects become extreme. If an astronaut were able to orbit just outside the event horizon of a supermassive black hole and later return to Earth, they might find that decades or centuries had passed outside while only a short time had passed for them. In this sense, black holes act as natural gateways to the future. Yet this strange relationship between gravity and time raises deeper questions. If time can slow down near a black hole, what happens at the singularity where gravity becomes infinite? Does time stop completely, or does it transform into something fundamentally different? Our current theories cannot yet answer these questions. General relativity predicts the existence of singularities, but it cannot describe their internal structure. To understand what happens there, physicists believe we need a theory that unifies general relativity with quantum mechanics. Such a theory is often referred to as quantum gravity. Developing quantum gravity is one of the greatest challenges in modern science. Several candidate theories exist. One of the most well-known is string theory, which proposes that fundamental particles are not point-like objects, but tiny vibrating strings. Another approach is loop quantum gravity, which suggests that space itself may be composed of discrete quantum units. Attempt to describe the structure of space-time at the smallest scales imaginable. Black holes provide one of the most promising environments for testing these ideas because they combine extremely strong gravity with extremely small scales. They may reveal quantum effects that cannot be observed elsewhere. For example, some models of quantum gravity suggest that singularities may not actually be infinitely small. Instead, quantum effects might prevent matter from collapsing completely. The core of a black hole could be a dense but finite region where new physics emerges. Other models suggest that the interior of a black hole might connect to another region of space-time through a wormhole. If such structures exist, they could theoretically link distant parts of the universe. Although these ideas remain speculative, they highlight how black holes serve as laboratories for exploring fundamental physics. But black holes are not only important for theoretical reasons. They are also extraordinary astrophysical objects that we can observe across vast distances. In recent years, astronomers have discovered black holes in a wide range of environments. Some exist in binary systems with companion stars, where the black hole pulls gas from its partner. Others wander alone through the galaxy after being ejected by supernova explosions. And at the centers of galaxies, supermassive black holes influence the motion of billions of stars. The study of these systems has revealed that black holes are far more common than once believed. Our own galaxy may contain hundreds of millions of black holes formed from the deaths of massive stars. Most of them are invisible unless they interact with nearby matter. Detecting them requires careful observation of their gravitational effect. Gravitational wave observatories are helping uncover these hidden populations. When two black holes merge, they produce a burst of gravitational waves that travel across the universe. These waves carry information about the masses and spins of the merging objects. By analyzing these signals, scientists can map the distribution of black holes across cosmic history. Each detection adds a new piece to the puzzle. And the puzzle is growing rapidly. As detectors become more sensitive, astronomers expect to discover thousands of black hole mergers. Some of these events may involve black holes that formed in the earliest galaxies. Others may reveal exotic systems that challenge existing theories of stellar evolution. In the coming decades, new missions will expand our ability to study black holes. Space-based gravitational wave detectors such as LISA will be able to detect mergers between supermassive black holes. Future telescopes may observe the motion of matter extremely close to Event Horizon, and improvements to the Event Horizon telescope may allow astronomers to capture sharper images of black hole shadows. These observations will deepen our understanding of how black holes grow and evolve. They may reveal the dynamics of accretion disks and magnetic fields near the event horizon. They may even uncover evidence of new physical phenomena predicted by quantum gravity. But perhaps the most profound lesson from studying black holes is how they change our perspective on the universe. They remind us that reality is far more complex and surprising than our everyday experiences suggest. Space can bend, time can slow, light itself can be trapped by gravity, and objects can exist that challenge the limits of our theories. Black holes demonstrate that the universe still contains mysteries waiting to be explored. They encourage us to ask deeper questions about the nature of reality. They inspire new technologies, new experiments, and new ideas, and they remind us that scientific discovery is an ongoing journey. Every answer we find leads to new questions, every observation reveals new possibilities, and every mystery invites us to look further into the cosmos. Black holes, once thought to be the ultimate endpoints of cosmic evolution, have instead become gateways to new understanding. Through them we glimpse the connections between gravity, quantum mechanics, thermodynamics, and the structure of space-time itself. In this way, the study of black holes continues to transform our understanding of the universe. And as humanity's instruments grow more powerful and our theories become more refined, we will continue uncovering the secrets hidden within these cosmic giants. Because the darkness of a black hole is not just emptiness, it is a frontier. Nature reveals themselves to those who dare to explore. And that exploration is only just beginning.